Okay, so our chapter right now, equilibrium, is about really looking into how what the makeup of objects and how these objects behave depending on the forces acting on them and their locations. And so what I want us to think about is situations like this, where we have a beam or something like this, and maybe you have two supports for it. And so if it's just a regular beam, you have two supports. These supports are going to have the same amount of force, or going to be applying like the same amount of force to keep this upright. But if you put, let's say we add some weight to this beam in the middle, it will still be even. But if we put the weight to the side, now all of a sudden one of these beams has to apply more force than the other. And this kind of thing can be really relevant for different engineering situations. And I took actually in college a whole class called statics that was on static equilibrium. There you can get a lot deeper into it than the analysis we're going to be doing in the next week or so. So anyway, let's take a look at this. It's relevant for situations like this where you have someone walking across a beam that's being supported by two supports here. They're called S1 and S2, and so they have a weight of 600 newtons. This beam has a weight of 500 newtons. It's 4 meters long, and we want to know how much force each of these beams have to support in order to keep this person upright. And so for all the problems we're looking at today, we're looking at one-dimensional problems in which we have this object is acting only in one dimension, and the forces are only acting up and down on it. Okay, and so we can use our knowledge of forces and torque to basically figure out, kind of work our way into what those forces are equal to. So the first thing we know is that we see that there's this much weight downward, right? The 600 newtons and the 500 newtons. And so that means there's a combined downward weight of 1100 newtons, which means these two forces here also have to be pushing up with 1100 newtons. And so the way that we approach that is we say we could do a net force equation. So we'll say, and the key is equilibrium, so instead of adding to be equal to MA, the forces need to add to equal 0. And so we'll say 0 is equal to, we'll say up is positive, so S1 plus S2 minus the 600 minus the 500. Okay, so we have an equation here that we can use. Now the problem is we have two variables in this equation, so we know that these have to add to be equal to 1100, but that's not enough. Okay, so the next step now is to think about rotation. So if this is an equilibrium, that means that not only are these forces balanced to keep it from going up and down, but that the net torque about any point is also balanced because it's not starting to rotate. There's no angular acceleration. So the trick here is that we can set the torque to be about any point. We could do the torque about this point, this point, this point, or this point, because the torque about all of those points is equal to 0. Okay? But not all of these points are good options. What I mean by that is that some are going to be more convenient than others if we want to find the one of these missing forces. So when we decide to do a net torque equation, we want to pick a point like here or here as our rotational axis, because what happens is then if we pick this as our axis, then S2 here doesn't provide a torque. Or if we choose this one as our axis, then that one doesn't provide a torque. And that makes it simpler for the solving portion. So we'll choose, it doesn't matter, we'll choose, let's say, S2 right here, okay, as our axis of rotation. So we're going to find the net torque about the point S2. And this is going to allow us to basically determine how hard this upward force needs to be in order to support these two downward weights, okay, and to prevent it from rotating downward. All right, so if the sum of the torques is 0, we have, remember, torque is force times radius times sine of the angle. Since all of these are perpendicular, then this is going to turn to 1 for all of them, so just the force and the radius. So 600 newtons times our radius of 0.8 meters. For this one, we'll say that counterclockwise is positive, so that would be a negative torque. this 500 is going to be at the center of the beam, so that'd be 2 meters away, so minus 500 times 2 meters. And then finally, S1 here is going to be a positive torque, causing it to rotate that way, and it's 4 meters away. So we can now solve this equation for S1, which then we can plug into there to get S2. So I'm going to go ahead and solve this right now. So we simplify it, we get that S1 is equal to 370 newtons. Now our next step, if we want to find out how much force this one has to supply as we put it into here, so we're going to say 0 is equal to 370 newtons for S1 plus S2 plus or minus our 1100 newtons. So we're going to solve this for S2 and get that S2 is equal to about 730 newtons. Okay, and so you'll notice that these two posts are applying different amounts of force on the beam, and the reason why is because this person here is closer to this side. Notice that each of them is at least supporting 250 newtons for half of the amount of weight of the beam, and they're supporting additional force for the person, and more of it gets carried to this side because the person is closer to this side. Okay, and this is an example of how you can use torque and forces to figure out kind of like some missing values, or just to figure out like where the forces are going to be strongest on like a beam or something. Okay, so we're going to look at 3 more examples now. So in this next example, we're going to find the torque. Sorry, not the torque, but the amount of tension in this cable right here. Okay, do you see there's a cable that's kind of supporting this crane, and there's a very massive weight right here, a smaller amount of weight right here, and then we're having to support it with this cable. And so the same approach here, and then there's a hidden force that we don't see, which is the upward force provided by this support right here. So we have an upward force there, a downward force there, a downward force there, and a downward force there. Okay, and so to approach this one, we're going to do the same thing. We'll say that some of the forces in the y direction have to add to be 0 since it's all balanced. And I'm just going to use 25. I'm going to use units of kilonewtons. So we have upward of, we'll call this just F, minus downward we have T, and we also have downward 15 and 25. So we could say that 0 is equal to F minus T minus 40 kilonewtons. Okay? And actually for this one, if we just want to find the tension, we don't even need to use this equation because we can actually figure this one out just using torque. Okay? If we set this to be our axis of rotation, then we have 3 forces causing a torque and only 1 unknown. So we can say, okay, that sum of the torques has to be equal to 0. We have torque from the tension that's going to be, this is causing it to rotate this way. The cable is pulling it this direction, which is going to be a positive torque. So we're going to say the force of tension acting 4 meters away minus this 25 kilonewton force on the other side that's 10 meters away. And then we have this other force, which is the actual weight of the beam. It's going to be located at the center of the beam. Or I guess in this case it's a little bit off center. And so that's also going to be negative. So that'd be 15 times 2. And so now we can solve this equation for T. So we'll get that the tension in this cable here needed to be 70 kilonewtons or 70,000 newtons to support the weight of these two things. And remember, it's also counterbalancing this upward force here. So this upward force here would have to be really strong because it'd have to be basically balancing out this 70,000 newton force here, this 15,000, and this 25,000 here. So it'd be like 110. And you could take this here and put it into that equation and solve for F and get that. Okay? Okay, so now in this next example, we see this rod here, this uniform rod. And we have 1, 2, 3, 4, 5 forces acting on it, and you'll see that 2 of these forces are unknown. Okay, and so the first question I have for you about this is, could we find F1, these 2 forces, could we find the magnitude of each of them, figure out how strong each is? just by using a net force equation, like the sum of the forces in the y direction, and setting it equal to 0, would that be enough to give us the value of each of these separately? The answer is no. We could find the combined value of them, but that's not very helpful. Okay, so we would need to use first a net torque equation. Okay, so the second question I have is, if we are going to do this, we want to find the strength of F2. Okay, if we want to use just one equation to find the strength of F2, where should we put our axis of rotation? I'll give you some options. You can choose A, B, C, or D. So or E. So which of these 5 options is the best if you wanted to find the magnitude of F2 just using one equation? Okay, so the answer to this would be to make the pivot at point C. So we would use this as our axis of rotation because F1 is located here, meaning it causes no amount of torque. Okay, which if we balance out these 4 forces, that will be enough to do so. Okay. Alright, the last question is to find out what the magnitude of F1. So let's say that we now find out that F2 is actually equal to 62 newtons. Okay. 62 newtons. Okay, so go ahead and find what F1 is. Okay, and you can do this using one equation, and you have 2 options here now. Okay. So to figure this out, you could either use torque or summing the forces. Okay, since we know now what all these forces are, we could use that to balance it out, or we could do a torque around any of these points except for C to figure out F1. And so we'll get here that F1 is 45 newtons, and if you did 42, because I'd written a 62 here and a 65, then that's good too. But basically I just did a net force in the y direction equation to figure this out. Alright, so we're going to do one last example. Okay, in this case we have a uniform rod with 2 masses hanging, and it's balanced slightly off center. Okay, and so we want to find the distance that this 0.2 kilogram mass is hanging away from this axis of rotation so that this whole system can be balanced. And so basically we have 3 forces providing a torque here. This force right here, this force right here, and this force right here. And we also have the force from the weight of the rod, and we account for that. We're going to place that at the center of mass of the rod is where we account for that. So if this total distance here is 0.9 meters, then the center of mass is going to be 0.45 meters away from the end, or 0.2 meters away from the pivot. Okay, and so for finding this, the easiest approach would be to set the axis of rotation right here, which means that we can ignore the upward force from this. Okay, we also can do this with one equation instead of 2 because we're just looking for that distance. So we're going to say, okay, the net torque around that pivot point has to be equal to 0. We have a positive torque from that 0.2 kilogram mass. So 0.2, so the torque is caused by its weight, which is mg. So 0.2 kilograms times g times the radius x, which we don't know, and I'll clean that up a little. So 0.2 gx minus this negative torque here of 0.5 kilograms times g for its weight times the distance away of 0.25 meters, and then plus we're going to have a positive torque from the actual weight of the beam since it's located right here, 0.2 meters away, and we'll say 0.122 kilograms times g for gravity times 0.2 meters away, and all of that adds up to be equal to 0. So now we can just solve this equation for 0. You can see the g's are going to drop out of the equation, and we're solving here for x. Alright, and so we get that the distance away is going to be about 0.503 meters, and so this is going to have to be about a half meter away in order to balance out this object right here. Okay, if this didn't have mass, then it would have to be further away, but because this beam has mass, it helps it out and allows it to be closer in. Okay, please let me know if you had any questions on this video.